Let's do some more practice with the chain rule and with our trig functions and their derivatives. So we'll start on this panel with some that are going to be just more straightforward chain rules. So you have a function inside a function. So remember that we're going to kind of think of this as cotangent of u. And so our derivative with respect to u, or with respect to x, is we're going to take the derivative of cotangent, which is going to be a negative cosecant squared. We need to know these from memory, of u, and then we're going to multiply that by the derivative of u, that inside function. So thinking of it that way, we're going to get our derivative dy dx is going to be a negative cosecant squared of our u is 5x cubed times our du, which is the derivative of 5x to the third. So using our chain rule, or our power rule rather, we'll get 15x squared. And we'll bring the 15x squared to the front to join that negative 1 and call that negative 15x squared cosecant squared of 5x cubed. Okay. Similarly, we know that f prime of the u is going to, well, I want to keep it with the x there. So with the x is going to be the derivative of secant is secant u tangent u times du, the derivative of that inside function. And so we're going to get secant of x squared times tangent of x squared times the 2x. And again, we'll bring the 2x in front so there's no confusion that it is not inside those trig functions. And that's going to be our derivative. And for a tangent, we're going to get that its derivative is going to be e to the u times du, the derivative of that inside function, the derivative of the exponent. So you get the same exponential back, e to the tangent x, times the derivative of the exponent, which is going to be the derivative of tangent, which is secant squared x. And that's probably would be better to leave just like that. If we kind of write that exponent a little taller, and then we can kind of squeeze the secant squared x underneath it. And for our derivative of cosecant, we're going to get negative cosecant u cotangent rather. Let me get that eraser up here. Negative cosecant u cotangent u times du, the derivative of that inside function. So even if you say it, it kind of, your brain will kind of pick up on what it's supposed to do there. So it's a negative cosecant of e to the x, cotangent of e to the x times the derivative of e to the x, which is e to the x. Probably better to bring that e to the x out in front with the negative sign, and then we get that is going to be our derivative. So let's go to the next panel, and we're going to do some three-linked chains. So here we're going to take the derivative. So you have to kind of train your brain to see those different layers of that function. So here is the innermost function. There is the middle function, is that exponential. And then our outermost function is going to be our sine curve. So we will get then that our dy dx is going to be, and we'll take the derivative of that outermost function, cosine, and leave the rest of it alone for now. Then progressing to the middle level, the derivative of 3 to the 4x, or the derivative of 3 to the u, is going to be 3 to the u times natural log of 3, and then we'll get our du after that. So this is going to be our, I'm sorry, not an equal sign, that's a times. So that's going to be 3 to the 4x. We have our natural log 3. And then finally, the last thing we'll do is a derivative of that 4x, which is the 4. So at the end of the day, we bring the 4 in front. The natural log 3 is kind of optional, because then if you write it Usually we probably would just leave it as cosine of 3 to the 4x, and then maybe it's going to be messy any way we do it, so I'm going to change my mind there and maybe put in some more parentheses. So either 4 times 3 to the 4x, or you could put that 3 to the 4x in parentheses, and then times our cosine of 3 to the 4x, and then maybe at the very end the natural log 3. There's no great way of doing that. Okay, next one, we're going to see our outermost function is the cotangent, and the middle layer is going to be our exponential e to the u, and our innermost function is going to be that 6x. So we're going to get f prime is going to be the derivative of cotangent is negative cosecant squared, and then we are going to have of e to the 6x, so we don't change anything with that, then times the derivative of e to the u, which is going to be that same exponential, so we're going to get that e to the 6x, and then finally times du, the derivative of that 6x, is going to be a 6. So we're going to get f prime of x. We can bring that maybe negative 6 in front. Probably the e to the 6x would go best next. Then cosecant squared of e to the 6x. Okay, and then our last one, so we're going to have our outermost function is going to be the 4th power here, and then the second level is going to be that secant, and the innermost one is going to be our 2x to the 3rd. So we're going to get g prime of x is going to be, we'll bring that 4 times the secant raised to the 3rd, and then we'll leave the 2x cubed alone. So now we're going to that second level, the derivative of secant, which is going to be a secant of, and we're going to leave the 2x squared as it was, and then we still have a tangent also of that same 2x squared. We don't change what's the angle or the argument of that trig function, and then finally times the derivative of the, oops, I made those squares, they should have been thirds. Let me see if I can fix those. Let me bring up that eraser. See if I can change that into thirds. We haven't taken that derivative yet. And then finally we're going to get the derivative of the 2x to the 3rd, which is going to be a 6x squared. So our derivative, see if we can figure out how to clean this up. The 6x squared will join the 4 and be 24x squared. Notice that we have a secant cubed and then another secant, so they will multiply each other and become a secant to the 4th of 2x cubed, and then the tangent of also 2x cubed. And I know you're tired of hearing it, but notice all of the trig functions have the same angle that the original did. Okay, very good.